Welcome to this lecture on the female reproductive system anatomy. Today, we are going to explore the incredible biological machinery that makes human life possible. We will look closely at the ovaries and the uterus, not just as static organs, but as dynamic structures that change over time. Understanding this system is fundamental to reproductive biology, family planning, and women's health. Let us dive in. To begin our journey, let us look at the foundational structures of the female reproductive system, the ovaries. Why do these organs matter so much? They are the master controllers of a woman's reproductive lifespan and hormonal health. Anatomically, they are paired, almond-shaped glands situated in the lower abdomen. They serve two critical functions. First, they act as endocrine glands, producing vital sex hormones like estrogen and progesterone. Second, they are responsible for folliculogenesis, which is the biological process of maturing and producing ova, or eggs. Without these organs, the entire reproductive cycle would not exist. Now that we understand what the ovaries do, let us look at how they manage their most precious resource. Imagine a bank account that you are born with, but you can never deposit money into it. You can only make withdrawals. This is exactly how the ovarian reserve works. The ovarian reserve is the total number of immature eggs, or primordial follicles, present in the ovarian cortex at birth. Throughout a woman's life, this reserve is continuously depleted through ovulation and a natural cell death process called atresia. Understanding this biological bank account is crucial for diagnosing infertility and understanding the onset of menopause. Before we look at the mathematics of fertility, we must understand the biological processes at play. The reserve we just discussed does not just sit passively. It undergoes folliculogenesis, the complex journey of maturing primordial follicles into fully developed ova. Interestingly, while many follicles begin this maturation journey each month, usually only a single high-quality egg is ovulated. What happens to the rest? They are lost through a natural programmed cell death process known as atresia. This continuous depletion through both ovulation and atresia is a relentless biological reality, occurring constantly throughout a woman's reproductive years. This concept of a depleting reserve leads us to an important mathematical model. We can actually predict a woman's fertility window by modeling this decline using an exponential decay formula. The formula is n of t equals n0 times e to the power of negative kt. Let us break this down. N of t represents the number of follicles remaining at a specific age, t, measured in years. N0 is the initial massive reserve of follicles, present at birth. The constant e is the base of the natural logarithm. Finally, k is the decay constant, which dictates how rapidly follicles are lost. As age increases, the negative exponent causes the remaining follicle count to drop rapidly, reflecting natural reproductive aging. Before we move on, let us see this formula in action with a concrete example. Imagine a newborn female infant born with an initial ovarian reserve of 1 million follicles. Clinical data gives us a decay constant of 0.05 per year. We want to find out how many follicles remain when she reaches age 30. We start by plugging our known values into the exponential decay equation. Multiplying the decay constant by 30 years gives us an exponent of negative 1.5. Evaluating e to the power of negative 1.5 gives approximately 0.2231. Multiplying this fraction by the initial 1 million yields our final answer. Physically, this means that by age 30, only about 223,100 follicles remain, which is roughly a quarter of the original reserve. Now that we have calculated the decline of the reserve, let us visualize the anatomy where this all takes place. On screen is a cross-section of the female reproductive system. Notice the central uterus and the fallopian tubes extending outward to the ovaries. Look closely at the ovary on the left. You can see the tiny primordial follicles resting in the outer edge, the ovarian cortex. Following the arrows, you see the progression of folliculogenesis. A follicle matures, grows significantly into a Graafian follicle, and finally ruptures to release an ovulated egg toward the fimbriae. This diagram beautifully captures both the static anatomy of the organs and the dynamic biological process of egg maturation and release. Having explored the ovaries, we now travel down the fallopian tubes to our next major organ, the uterus. Why is the uterus so critical? It is the only organ in the human body capable of expanding massively to accommodate and protect a growing fetus. Anatomically, it is a hollow, pear-shaped muscular organ, securely located in the female pelvis, nestled between the bladder and the rectum. The fallopian tubes connect the upper part of the uterus directly to the ovaries, providing a clear anatomical pathway for the ovulated egg to travel. If we take a cross-section of this remarkable organ, we see that the uterine wall is built of three distinct anatomical layers. The outermost layer is the perimetrium, which provides a protective outer boundary. Beneath that lies the myometrium. This is a thick layer of smooth muscle tissue, responsible for the powerful contractions during childbirth. Finally, we have the innermost layer, the endometrium, which is a specialized mucous membrane. Understanding these specific layers is essential for medical professionals when diagnosing conditions like abnormal uterine bleeding or endometriosis. Building on our understanding of uterine anatomy, let us focus specifically on its innermost layer, the endometrium. Think of the endometrium as a highly specialized, dynamic incubator. It is divided into two parts, a deep basal layer that remains constant and a superficial functional layer. Every single month, this functional layer thickens to prepare a fresh, nutrient-rich bed for a potential fertilized egg. If an egg arrives, it has a soft, welcoming place to implant and grow safely. If no pregnancy occurs, this thickened layer sheds and the cycle begins anew. This cyclical thickening is the absolute prerequisite for embryo implantation and human survival. This dynamic thickening of the endometrium can actually be quantified. During the proliferative phase of the menstrual cycle, the tissue grows steadily under the influence of estrogen. We can model this using a simple linear equation. E of t equals E0 plus R times t. Let us define these terms. E of t is the total thickness of the endometrium on a given day, t. E0 represents the baseline anatomical thickness, immediately after menstruation is finished. The variable R is the daily growth rate of the tissue, measured in millimeters per day. As time increases, the thickness increases linearly. By tracking this, doctors can easily identify abnormalities and ensure the uterus is preparing properly for pregnancy. Now that we have our linear model, let us apply it to a clinical scenario. Imagine a patient undergoing fertility monitoring. Ultrasound reveals her baseline endometrial thickness is 2 millimeters. Her tissue grows at a steady rate of 0.5 millimeters per day. We need to calculate her total endometrial thickness after 12 days of continuous growth. We substitute our known values into the linear equation. First, we multiply the daily growth rate of 0.5 by 12 days, which tells us that 6 millimeters of new tissue has grown. We then add this new growth to the baseline of 2 millimeters. The final answer is 8 millimeters. Physically, an 8 millimeter thickness is considered highly receptive, creating the perfect anatomical environment for an embryo to implant successfully. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that the ovaries are not just hormone producers. They act as biological vaults, holding a finite ovarian reserve. This reserve depletes exponentially over time, dictating the natural reproductive lifespan. Second, we explored the uterus, focusing on its dynamic inner lining, the endometrium. We saw how the endometrium grows linearly each month to create a receptive environment for embryo implantation. By understanding both the exponential decay of eggs and the linear growth of the uterine lining, you now have a solid, quantitative grasp of female reproductive anatomy. Excellent work today.